Hi,
Hello.
I'm Cameron, this is Maria, and Alexi is filming, and this is our electrical impedance tomography system design. So unfortunately, with the PCB, we didn't get everything working. We only got our power supply and voltage regulation working, but with the breadboard, we've reconstructed all the circuitry and everything works perfectly, so we'll go through that. For our design, we're given up to 4 9-volt batteries to power our PCB. However, we require plus minus 12 and plus minus 15 volt rails for the operation of our circuit, as well as a ground rail. As our electrical impedance tomography system is to be used on people, our signal generator needs to produce a sinusoid centered at 0, so to ensure no harm due to DC offset. So we're using all 4 provided 9-volt batteries in a dual supply configuration, that is plus or minus 18 volts, which negates the need for any DC offset adjustment circuitry necessary for a single supply config. As we see here on our PCB, our 78 series regulators successfully stepped down voltage from plus 18 to plus 15 and then plus 12 volts.
Okay.
There's the 12. And there's the 15. It's just a little bit low. I think maybe our batteries have discharged a little bit. And similarly, our 79 series regulators successfully stepped down voltage from minus 18 to minus 15 and then minus 12 volts.
Wait, no. For the function generator, after considering several options including a low-cost DDS function generator, ELEC3803, the 555 timer chip, and a 3-stage differentiator, we selected for our design the ELEC3803. This chip allows us to generate a sine, triangle, and a square wave. The square wave is on a separate output, pin 11, and the sine and triangle waves can be selected via a switch, pin 2. This was not possible with the 555 timer chip. The frequency of the output wave depends on the value of the capacitor connected between pins 5 and 6 and the resistor connected in pin 7. As we want to be able to control this frequency externally, we put a variable resistor in pin 7. The frequency will be given by 1 over RC. The values of R and C were determined accordingly to our required frequencies, ranging between 1 and 5 kHz, taking into account that temperature stability of XR2206 is optimum for R ranging between 4 and 200 kiloohms, and that the recommended values for C are between 1000 picofarad and 100 microfarad. Finally, we picked the values of C equal to 100 nanofarads, and R is a 1K resistor in series with a pot of 100K. To control the output, we will use a variable resistor in pin 3, since according to the datasheet, our amplitude is inversely proportional to the external resistor connected to pin 3. For sine wave output, amplitude is approximately 60 millivolt peak per K of R3. For triangle, the peak amplitude is approximately 160 millivolt peak per K of R3. Taking into account that we want an output voltage of amplitude varying between 2.27 and 4.54, that with the gain of the current pump will indeed give us an output current between 0.25 and 0.5 milliamps, we choose a value of the resistor at pin 3 as a 100K potentiometer. Some of the reasons why we chose this IC are very low distortion, in fact less than 1% at frequencies lower than 100 kHz, that is well above our operating range, a much better performance than the 555 timer chip and the 3-stage differentiator. Good thermal region of operation, although the other options we consider also had this feature. Is to find the components needed to build it. This was actually a key aspect with respect especially to the 8038 or the low-cost DDS function generator. The inability of finding the components required for those designs in the time required made us having to discard those options. Possibility of using a dual supply, making it easy to center the signal at 0 DC voltage.
As we can see, when we test it on the breadboard, we get a sine wave, a triangular wave, and a square wave. We can indeed change the amplitude and frequency of these waves. When looking for a current pump, it should fulfill the following requirements. The current amplitude should be as large as possible without compromising safety. Good performance over the whole working frequency range between 1 and 5 kHz is required. A minimal common mode voltage into the measuring circuit is also required, and there should be security against electric shock. Considering these facts, we compare between different topologies to decide the best option for an EIT system. Once we compared between the different topologies, we got to the conclusion that the ISSA improved whole and current pump was the best option for our circuit, as it is the one with the best performance. That is, output impedance and current magnitude. Once we have decided what topology of current pump we are going to implement, the next part was to choose the components. Dealing with the operational amplifier, we first decided to use the op-amp ELEC3803 because it accepts the range of voltages that we are aiming to apply, and its maximum output current is 20 milliamps. It is more than enough for us, as we only want to generate around 0.5 milliamps. The problem that we had with this op-amp is that it was really difficult to find it in a physical store, and we had to buy it online, which took several days. Time that we hadn't, as we need to build the system in 1 week. So, due to the purchasing problems, we needed to discard this option. As we were having troubles when finding the components in the store, now one of the first requirements we are looking for in an op-amp is that we can buy it in a physical store so that we have time enough to buy and build the circuit. That is why LM741 became one of our options. We found in the bibliography that it had been used for doing experiments on biomedical applications with EIT systems with good performance, so it would be probably a good candidate for our project. The supply voltage has a maximum of 22 volts, so that we can achieve to run our op-amp easily. Furthermore, if we look at its operating temperature, we can see that it has a minimum of minus 50 degrees, so we would be able to make it properly function inside the fridge. We managed to build a current pump with this operational amplifier. However, in the lab, they recommended us to use the op-amp 2134, as they said that the performance was much better. So we followed the advice of our tutors and we changed the op-amp when designing the PCB. Once we have chosen our op-amp for the current pump, we need to build the current pump.
Once we have chosen our op-amp for the current pump, we need to build the current pump. As we have seen, we have chosen the Holland current pump as final topology for the project, where the gain is R2 plus R3 over R1 times R3. We have as requirements that the ratio between R5 and R4 is equal to the ratio between R1 plus R3 over R1, and to have resistors with a small tolerance. Having all of this into account, we choose as resistor values R1 equal to R2 equal to R5 and to R4 and equal to 100 Ks, and R3 equal to 10 Ks. As it has an acceptable value for the gain, we get a gain of 1 times 10 to the minus 4, and it accomplishes the requirement for the Holland pump.
Now I'm going to talk about the schematics and the PCB design. On the bottom layer, we will use it for the power supplies. We will need thicker rails for power. We chose 0.8 millimeters. In the top layers, we will put the circuit connections with a width of 0.4 millimeters because we don't need it as big as for the power supply. We will include a polygon board to provide all the components the same ground, and we will try to segment the areas to separate the power supply, the voltage regulators, the signal generator, and the current. We will use headers for super protection between each of the areas. However, we forgot to include one between the power supply and the signal generator.
We included a voltage follower within the current pump for protection for the patient and circuit output. We also tried to include fuses between the power supply and the voltage regulator to prevent the circuit to get damaged due to a wrong powering, but we didn't find the specific ones required. The limitations and major obstacles we found in our design were: we wanted to include fuses for further sacred protection, but the ones we found wouldn't fit on our PCB because they were too big. They were not meant to be used on PCB design. We wanted more headers for protection between the voltage supply and the signal generator to segment the areas nicely. Our voltage regulators require at least 2.5 volts above the voltage they're dropped to, which is a very narrow range before the batteries require replacing, since we're only allowed to use 4 9-volt batteries. In future models, we could use plus and minus 27 volts, which would last longer before needing replacement. The costing of our whole design was $19.99 for the XR2206 used for the function generator, 2 op-amps 2134, which were $2 each, making a total of $16 in op-amps, 2 78 voltage regulators that were $0.906 each, making a total of $1.812, 2 79 voltage regulators, which were 0.96 cents each, which make a total of $1.92. The resistors in total costed us 55 cents, and the capacitors $3.15. All the pots had a total cost of $12.5.